So, welcome to this class on hardware security. So, we shall be continuing our discussions on fault attacks, and in fact, today we shall be starting our discussions about possible countermeasures against fault attacks. So, we shall be starting with countering fault attacks using detection schemes, which is the most common fault tolerance technique that has been adopted for cryptography, and it has been given a special name which is called as concurrent error detection or CED schemes. We shall be discussing about certain forms of them, and in particularly we shall be focusing about a parity based implementation for AES algorithm, and we shall be discussing about time redundancy countermeasures and also try to kind of reflect upon the uniform fault models as opposed to something which is called as biased fault models, which is very prevalent in present day fault injections. And motivated by by this model of biased fault attacks, we shall be defining something which is called as differential fault intensity attack, which is another class of fault attacks. And finally, we shall be discussing about vulnerabilities of detection based schemes versus DFIA kind of attacks. So, to start with, right, I mean it is very important, as we have seen, right, to kind of address fault attacks, because fault attacks can be devastating for cryptographic implementations. So, right, the question is whose fault is it? So, like naturally, right, there can be a debate about that, like is it the flaw in the algorithm or is it the flaw in the implementation. So, as opposed to like side channel attacks, which is often blamed to the implementers, in context of side channel, in context of fault attacks, right, I believe that there is a little bit of share for the algorithm designers also. So, so it is, like, so the question is, right, I mean rather than like whose fault it is, probably what is more important is how we can build our countermeasures. So, the first thought that comes to our mind is that we know that fault tolerance is a problem which is not only for cryptography. For sure, for cryptography it has a very devastating effect, but at the same time can we adopt classical fault tolerance in the context of fault attacks, in the context of cryptographic scenarios. So, therefore, right, first let us try to understand what is meant by detection based countermeasures. So, this is also known as concurrent error detection techniques, or CED as it is abbreviated. It basically uses various kinds of redundancy to detect faults. Redundancy is a very important like technique or trick to basically counter fault attacks, or basically it's a very popular fault tolerance technique which we also have tried to adopt in the context of cryptographic implementations. So, we have already seen as we will see, right, gradually, that these kind of techniques are vulnerable to attacks in the comparison step itself, because there would be an explicit comparison step, and that can be often like targeted by the attacker. So, when we discuss about such kind of detection based countermeasures, therefore, tacitly we will assume that the comparison step is flawless, right. We will assume that it basically gives you a correct comparison. So, we will as we proceed, right, we will see that detection based countermeasures are also vulnerable to what are called as biased fault injections or biased fault attacks. And so, what is the basic principle of CEDs? So, the basic principle of CED is very straightforward. It, as this diagram shows, it is essentially based on redundancy. So, like usually what we do is we are given a plain text, we get a ciphertext, and we were releasing the ciphertext in the network. But here, before we release that, we will do a double check. So, for example, like we can have a duplication with respect to hardware, and we can kind of do this encryption in two different devices, and then we compare the corresponding ciphertext. If they match, then I will give you the output. The idea of the assumption is that like it is basically, right, we are assuming kind of tacitly that it is kind of improbable that I will be inducing the same fault in both the cases, which will lead to the same ciphertext. So, later on we will see like this probability is not very low in many real life scenarios, but based on the assumption that like that all faults are equally probable, because like for example, suppose you have a 128 bit state in AES, and if I assume that all the faults, that means there are 2 to the power of 128 possible faults, or maybe 2 to the power of 128 minus 1 possible faults, because like 0 is not a fault. So, if I just exclude that, even if I exclude that, right, there are huge number of possible faults, and if I assume that all of the faults are equally likely, then the probability that 2 fault injections will essentially lead to the same fault is really small. Okay. And therefore, right, this assumption is based on this fact Likewise, right, we can also do not only the redundancy with respect to encryption, but we can also do redundancy with respect to the opposite operation, that is with respect to like we can do in this way, like we get a plain text, we apply a ciphertext, and then we take the same ciphertext and then we apply decryption, and then we make a check in the plain text, right, which with the check that whether the same plain text has been obtained back. So you can like apply different forms of redundancies, and we will see that there are huge number of possibilities. I will be trying to talk about some of the important ones in today's class. So first, right, the most obvious countermeasure would be a hardware redundancy, and as we know, right, hardware redundancy means that I will duplicate hardware and I will detect fault by comparing the output of two copies. So there are two copies, and I would like to kind of redo the operation, and I will check. Naturally, right, there is a 200% area overhead because I am kind of duplicating the hardware. But at the same time, right, because there is a 2x, like if it was x, now it is 2x basically requirement of the hardware. So now there is another alternative strategy which can be useful, particularly, right, to prevent bypassing by injecting the same fault twice. Suppose, right, the adversary is trying to inject the same fault and is able to inject the same fault twice, then he would be able to kind of bypass such kind of countermeasure. So another possible or interesting solution which was proposed is depicted or illustrated in this diagram. So the idea is that I take like I have got two data paths, data path 1 and data path 2, or data path A and data path B, and then what I do is I basically do the encryption in data path A and data path B by kind of doing intermixing. For example, what I can do is I can in the classic redundancy, right, basically I take these states and I do an operation. I then in the second data path I kind of take this and do the operation and make a check here. But here what I will do is that I will kind of take some states from this this configuration, and I will take some states of this configuration, and then I will mix them. So as you can see, right, here I have kind of mixed them, and the remaining thing, for example, here there are some white bytes which has been taken from this below state matrix, and there are some dark state bytes which has been taken from the top state matrix, and I develop like the top matrix, which is kind of a mix of the top these two state matrices. And likewise, the remaining things like the like the things which are not taken from here and the ones which are not taken from here constitute this state matrix. Okay, and then I do a usual operation. You can already easily understand that if this and these are always matched, then I should again like get the same encryption or same operations for both of them. But what is the like advantage of doing that? Remember that the fault attacker, right, is trying to kind of bypass it, and therefore, right, if it kind of like has a knowledge like, okay, I will be trying to corrupt a specific byte, for example, where the chance of corruption is more, the chance or the probability that I kind of inject the same fault in the other pair is also probable, right, means probably doable. But at the same time here it becomes more difficult because of this mixing. Okay, so it is kind of more difficult for the attacker to control his fault injection to bypass such a strategy. Okay. And therefore, right, this is an interesting possible countermeasure, but at the same time, right, this also requires a significant amount of overhead in terms of resources. So therefore, right, I mean so this is like a depiction of how the hardware redundancy looks like. So you can as you can understand, right, there are two encryption bodies, and I am kind of comparing the results from two encryption. So therefore, the hardware overhead is definitely because of two encryption blocks that I am posing in my circuit. So the other possible strategy would be what is called as time redundancy. So in time redundancy, we basically compute the same function twice. So therefore, the duplication is not with respect to resource or hardware, but with respect to time. So therefore, right, I expand time, and therefore I do it in say 2 time steps, and again I do the check. For example, here I take the input, I obtain the encryption, and therefore the previous output, right, is kind of is basically stored in a register. You basically store the previous output in a register, and then you repeat the encryption. Okay, so you basically repeat the encryption, and then you get the same ciphertext, and then you kind of compare that whether the previous ciphertext is same as the present ciphertext. If they do not match, then you raise a flag. Naturally, right, there is less or negligible area overhead, but the throughput is affected. Now, in order to alleviate both the throughput as well as the resource requirement and get the advantage of timing redundancy, there was an interesting proposal which was published in IEEE Transactions on Computers in 2008, This technique is what is called as a double data rate or DDR. Now, DDR is an alternative strategy which is suitable often for pipeline data paths targeting operations which are not the critical path of your design. Okay. So, for example, what I am let me kind of illustrate this by this particular picture. Suppose you have got a pipeline 32-bit S box. Okay. So, remember that every state, right, of the AES matrix essentially is constituted of say 4 columns or 4 rows of 32 bits, and what I would like is that I would basically try to kind of like perform S box on each of the bytes of the state matrix, right. So, therefore, right, what I do is basically I take my state matrix and try to do them one by one. So, therefore, this is my state matrix. If you remember, right, this is my state matrix of AES 128, and I kind of take each of the rows of the state matrix separately. Now, each of the rows again are made up of 4 bytes, and that is why, right, 4 into 8 we have got 32 bit S box. So, therefore, the S box essentially is also at the same time pipeline, which means, right, you can perform several S box computations simultaneously. Okay. And again there are like 4 individual S boxes S box operations. Okay. So, this is kind of a pictographical overview on how the S box looks like here. So, now the key point of double data rate computation is that let us like try to perform the AES round like rather than, so in the usual pipeline I will basically perform the AES round in one single clock. Okay. So, there will be like for say what I will do is rather like I will be expending 4 clocks, because I will be like taking 1 clock for this, maybe another clock for this, another clock for this, another clock for this. Okay. So, now what I will do is rather than like I will basically try to reduce the number of clocks by operating this at both the positive edge as well as the negative edge. Okay. So, that would imply that what I will try to do is, for example, I will try to kind of operate these 2, that is alternative like stages in the pipeline in a specific clock edge, maybe the positive clock edge, but on the other hand, right, the other 2 I will try to operate them at the negative clock edges. Okay. So, I will basically try to kind of interpose them in this fashion. Okay. So, if you observe this diagram here, so this is my like state row say D1. So, this is the first row. I basically operate them like here as this arrow shows, maybe like I just operate them here at the positive edge, and in the negative edge I basically start operating this. Okay. As you can see that there is a forwarding here from D2. Okay. So, therefore, right, in the first stage I basically do both D1 and D2. Okay. So, I am basically, because in the first clock cycle, if you see, right, the first clock cycle is made up of this, here I am doing D1 and here I am doing D2. Okay. So, basically I am performing D1 here and I am performing D2 here. So, that kind of like helps me that to do like both D1 and D2 in one clock cycle. So, what is the advantage of this? The advantage is that I am basically reducing the number of clock cycles. Okay. Of course, right, there will be a cost or like an effect on this will be on the critical will be on the frequency of your clock, that will be affected. But as I say that assuming that this is not like exactly in the critical path, so I would expect that there would be a kind of like a small effect on the critical on your frequency, but not a significant one. Okay. So, because like it is not in the, I am assuming that this part of the circuitry is not in my critical path. Okay. So, therefore, right, I mean if that is so, then the advantage here is quite evident, because now since you have basically reduced the number of clock cycles, you have now some extra clock cycles. Now, what we will do is that in those extra clock cycles we will be doing a redundant computation. Okay. So, this basically will have a good effect on like redundancy as well as throughput. Okay. So, you can see here what I will do next is, in the next clock cycle I will start processing of D3. So, I will kind of forward D3 to this block and I will forward D4 to this block, and again I will repeat this process. Okay. So, I will be doing D3, D4, and remember that D1, D2 is going into the next stage of the pipeline, because this S box is pipelined. Okay. So, now what happens is, in the next clock cycle I basically start doing a redundant computation of D1, D2. Okay. So therefore, right, I mean, and again in the next clock cycle I do a redundant computation of D3, D4, and then I kind of verify whether it kind of matches with my previous computation. So here I basically do a match, and here also I do a match. So basically I am kind of doing, you know, like redundancy, but at the same time, you know, like you are essentially doing it simultaneously. Okay, so therefore, you know, like what we, so therefore this is essentially, you know, like the redundant blocks, and as you can observe that, you know, like there is, so you can observe that as the number of cycles are halved, the extra cycle can be used for redundancy. Okay, so this is essentially where you are doing two redundant computations. So these are the redundant computations. Okay, so we can generalize this process, of course, and you know, like pretty much this can be generalized for any pipelines where this condition is satisfied. Okay. So there is another interesting improvement on redundancy, and that is called as hybrid redundancy. So in hybrid redundancy, right, there are generally two forms of proposals. In one form, they kind of assume that in a chip, right, we both have encryption and decryption, because normally a chip would probably work as a transceiver or as a part of transceiver. So there will be, you know, like both an encryptor as well as decryptor. So if it be so, then what we can do is that we can leverage that, and we can use the encryption block and the decryption block to make a check. For example, right, I will take an input X, I will encrypt it, I will give it Y, and then I will kind of put Y to the decryption engine, and I will kind of decrypt it, and I will verify that whether it matches with my first plain text. Okay. Now there is another interesting proposal which is called as recomputing with permuted operands, or repo. Okay. So this particular style of design, right, is essentially based on, again, suppose we target the encryption process, we basically try to kind of study a useful permutation for encryption. Okay. For example, you can see that this is an example that we illustrate here with respect to AES. So if you, for example, consider the state matrix of AES, suppose the plain text of AES, and apply a permutation as shown here. Okay. So in this permutation, you can see what has been done is that, so you know, like it's kind of so basically if you observe here that this is your state matrix, like showing the 0th row, 0th column, first column, second column, and third column. Okay. And the permutation basically, and it's an invertible permutation, is basically where you do a you know, like cyclic left shift. So basically, as you can observe here, the 0 1 you know, like basically kind of shifts over here, the 0 2 shifts over here, the 0 3 shifts over here, and the 0 1 comes over here. Okay. So you basically do a corresponding shift. Okay. Now if you do this shift, right, then what the property is that, and if you denote it by, say, the permutation P, for example, then if you basically take a state matrix XS, for example, and if we apply the AES round, and then you apply this permutation, it is the same as if you take the state S, apply permutation, and then apply the AES round. Okay. So this would give you the same result in both the cases. So the advantage here is that you can easily kind of, once you have this kind of property, then you can take this and you can like use it to kind of develop an architecture where rather than having two encryption and decryption blocks, now you have got two parallel paths. In one, you basically just do a normal operation. In the other case, you basically perform this permuted operation. Okay, that means you basically perform a redundant operation with this permutation. So you take the state X, you basically permute it, you apply encryption, and then you apply the inverse permutation. So you should get back, because you are applying P inverse on AES round and PS, you should get the same as that of your original output. Okay, and then you match that and you see whether there is an error. So this design, right, apparently has got a very good throughput with respect to most of the attacks that we have exploited, like single byte faults, for example, and it has got an area overhead of around 20% for an iterated AES implementation. Okay, so therefore it is a very nice trade-off between overhead and fault tolerance. So this paper was published in DAC in 2012, and this is a reference corresponding to this work. So now there is another very important class of redundancy, and that is called as information redundancy, and it is based on error detection codes. Okay. So the idea here is that I take an input text and I perform an operation. So I basically have got some kind of like check bit generator, and the check bit generator basically like is used to predict some check bits that would happen after this computation. So, therefore, I basically take the check bit again apply the check bit generator after the operation, and then I basically make a match whether my predicted check bit matches with my with the output of the check bit generator after the actual operation has been done. Okay. So, therefore, right, I mean one of the very common forms of such kind of checks, right, is basically what is called as parity based checks, okay, where we basically perform parity. The other common form of checks is what is called as residue based checks. For example, we have heard of CRC and stuff like that, okay, and it can be applied at different levels. You can kind of adapt it for word level, byte level, or nibble level as your requirement. So, therefore, right, I mean this kind of gives a very very optimized design, because as you can understand that if you want to, for example, calculate the parity, you can have very efficient design architectures for doing so. But at the same time, right, you do not get 100% fault coverage, you essentially get much lesser compared to that. So, here is an example of trying to do a parity based code for AES, and I will not go into all the details. I will leave few things for you to kind of think over and as a kind of exercise. For example, the shift row is very easy, because you know that if you have got a parity bit of the state matrix. So, parity is like very easy to implement, because what I can do is I can it's very easy to kind of adapt it for AES, because what I can do is I can adapt the parity for every byte of the AES matrix. Okay. So, what I can do is basically I can take the AES state, and for every byte of the AES state matrix, okay, like for this byte or so on, I basically can have a corresponding parity bit. Okay. So, I can have a parity bit like Pij. Okay. So, therefore, right, I mean as you can understand that for shift row, right, it is very easy, because if you have got a parity state matrix, so let me call this state matrix with parity as parity state matrix. If I apply a shift row, then this parity state matrix state values will just get shifted accordingly. Okay. So, it is pretty easy to adapt. Likewise, but the hardest thing, right, is probably for the S box, because of the S box, the fact is that the S box is a nonlinear transformation. So, therefore, right, what is done is that we basically kind of alleviate this by kind of increasing the storage. Remember that the S box, right, is basically a storage where I have got 8 bits of input, right, I have got 8 bits of input and I have got 8 bits of output. That was my usual AES S box, right. So, now what I do is basically I keep an extra check or extra bit, and this is one extra bit that I keep, and this is a parity bit. Okay. So, again I have got 256 possible locations, because 8 bits can have 256 possible values, but then, right, the table becomes 256 cross 9. Okay. So, previously it was 256 cross 8, and now because of this parity storage it becomes 256 cross 9. Okay. And that is not I mean probably it can be afforded, and therefore, right, we are expanding the S box to 256 cross 9, and by adding this output parity bit we can propagate incoming errors rather than having to check explicitly. Okay. So, but however, right, it is interesting to see how it works for the mixed column operation. Okay, because in mixed columns, as we know that we have basically performed the Galois field operations. Okay, and here are some equations for doing so for mixed columns of AES. So, let me try to kind of work this out and see whether we can understand how these equations are derived. Okay. So, basically, right, I mean what I will do is basically I will take the AES state matrix. Okay. So, imagine that I will be just considering like one column of this, and the same thing will be applicable for all other things. So, let me consider this as S0, S1, S2 and S3. Okay. And we will be applying the matrix on this. So, remember the mixed column matrix, it has GF2 power of 8 elements, 2 3 1 1, 2 3 1 1, 2 3 1 1. Okay. So, now so let us consider the effect of, so basically like if I multiply this, right, and just consider this column, then it is 2S0 plus 3S1 plus S2 plus S3. Likewise, this is S0 plus 2S1 plus 3S2 plus 3S2 plus S3, and likewise this is S0 plus S1 plus 2S2 plus 3 S3, and this is 3 of S0 plus S1 plus S2 plus 2 S3, right. So, now if you just consider 2 into S0, let us just observe this with respect to parity. Okay. So, therefore, right, let us consider that S0 is denoted as the byte A7 x power of 7 plus A6 x to the power of 6 plus A5 x to the power of 5 plus A4 x to the power of 4 plus A3 x cube plus A2 x square plus A1 x plus A0. Okay. And the parity of A0, okay, is nothing but A7 plus. So, all these pluses are XORs, they are GF2 operator additions, A7 plus A6 plus A5 plus so on till A0. Okay. So, now if I calculate 2 into A0, so in polynomial notation this is nothing but x multiplied with A7 x to the power of 7 plus so on till A0. So, therefore, I will have A7 x to the power of 8 plus A6 x to the power of 7 plus A5 x to the power of 6 plus A4 x to the power of 5 plus A3 x to the power of 4 plus A2 x cube plus A1 x square plus A0 x, right. So, now remember that this x power of 8 has to be reduced, and our polynomial was x power of 8 plus x power of 4 plus x power of 3 plus x plus 1. Okay. So, what we will do is basically we will basically substitute x power of 4 plus x cube plus x plus 1 instead of x power of 8, and that will basically leave us with with this, right. We will basically start with a 6 x to the power of 7, and this will basically affect only the 4th degree polynomial, the 3rd degree polynomial, and this basically, right. So, therefore, I will have A6 x to the power of 7 plus A5 x power of 6 plus A4 x to the power of 5 plus, right, we will have A3 plus A7 x to the power of 4 plus A2 plus A7 x to the power of 3 plus A1 x square plus A0 plus A7 x, right, plus A7, because there is a constant plus A7. So, therefore, what is the parity of 2A0? The parity of 2A0 you can see is A6 plus A5 plus A4 plus A3 plus A7 plus A2 plus A7 plus A1 plus A0 plus A7 plus A7. Okay. So, we can do a bit of cancelling, and we can see that, for example, A7 will get cancelled here with A7. Okay. Likewise, this A7 will get cancelled with this A7. So, we will have pretty much all the terms A0, A1, A2, A3, A4, A5, A6, but only not A7. Okay. So, I can write this as the parity of A0 plus A7, right. So, therefore, the parity of this column can be easily written in this way, and also note that the parity of 3S0 can be easily derived as the parity of S0 plus the parity of 2S0, because parity is linear. Okay. And therefore, I can write this as parity of S0 plus parity of S0 plus A7, and that is just A7, right. So, therefore, right, if I want to calculate the parity of this column, so let me just write here as a big parity. Okay. So, then right, every element here will basically, for example, have like 2A0. If I just consider this, for example, 2A0, this will be parity of S0. So, let me write this as like parity of S0 plus, since I am doing 2S0, so there will be an S0 7. Okay. So, there is the 7th bit of S0 plus 3S1 will be the 7th bit of S1, okay, plus parity of S2 plus parity of S3. Okay. and this right is if you just little bit of rearrange. So, similarly we will get similar stuff for the other 3 bytes. So, this will be nothing but parity of S0 plus parity of S2 plus parity of S3 plus S07 plus S17. Okay. So, now if you just like go back. So, remember this equation. So, similarly we will have for the other possible things here. So, you see you get this, right. So, this is the 3 parity bytes plus the 7 bits which has been XORed. Okay. So, likewise you get for the other 3 things also, 3 bytes also. Another very interesting thing is that if I like kind of XOR the parity of these 4 bytes, for example, if I take P0, so I am just leaving out the J for simplicity, P0 plus P1 plus P2 plus P3, okay. Then you observe that this is equal to, if I just add up, right, then this S07 will get cancelled up here, S17 will get cancelled up here, S2J will get cancelled up, this will get cancelled up. So, pretty much this entire stuff will get cancelled up. Okay. Here also you can see that P0J and P0J, and there will be like another P0J. For example, the 2 of them will cancel up and only 1 of them will stay. Okay. So, therefore, right, and similarly for all the other 3 things. So, the parity right of this column does not change actually. Okay. And that is a property of the mixed column. I mean, and you can verify this very easily without performing any complicated Galois multiplication and so on. Okay. And that can lead to a very efficient check using parity. Okay. So, this is kind of depicted here, that you can use this parity prediction logic, and then you basically like predict the parity output, and then you can compare after using this logic. Okay. So, now what is again like because of parity, we know that this is not giving you like 100% coverage, and therefore, right, it can lead to like kind of reduction with respect to the overall coverage that you can obtain. Okay. So, what we will see is next, right, is how we will kind of like improve this by using the technique of now linear codes, and also, right, we will see about the bias fault injections, and also like how to perform what is called as differential fault intensity attack in the next class. Okay. So, thank you.